Systemd's nuts and bolts, a visual guide to Systemd. If you're an intermediate or advanced Linux user or sysadmin, you might have felt an odd fascination with the myth of Systemd. I invite you to this deep dive into Systemd's nuts and bolts. I'm not gonna beat around the bush. It's a hairy business, it will be hard, but I promise juicy and satisfying rewards if you keep it up. Let's start by uncovering the D of Systemd, the secret sauce that doesn't get the love it deserves. Dbus. Image description. Unmasking Systemd reveals dbus. Warning. This guide starts from Systemd's internals and only towards the end reaches the user-facing interface. By this we aim for a deeper, bottom-up, solid understanding. Readers in urgent need of getting familiar with Systemd are advised to look elsewhere, but feel free to skim and look at the pretty visual graphics, whose likeness is yet to be replicated elsewhere by any other Systemd guide. Don't miss the bus on this one. So, what is this dbus thing? Dbus, short for desktop bus, is a high-level message-passing mechanism for inter-process communication. APC. If that sounds like a mouthful, think of it as a fancy, typed remote procedure call, RPC, protocol, not unlike gRPC, GraphQL, or 0MQ, but heavily optimized for processes talking to each other on a single machine. Originally designed to keep everything in sync on desktop environments like GNOME and KDE, its usefulness has expanded to all sorts of system services. Sure, you could roll your own IPC with a log file and a lock, or a mess of Unix sockets, but you'd have to invent a protocol and a server to manage it all. Dbus gives you a standard framework for this, and it's typically implemented over those very same Unix sockets. Dbus also pioneered the concept of service activation, a concept eventually extended and extinguished by Systemd itself. Systemd later created a similar new trick, socket activation. More on those later, but it's basically about performance. Downsides of dbus: it's a bit verbose, a bit like Java. More on that later, and Linux only. But then again, Linux is the best OS in the world, so it gets a pass. Spoiler alert, Systemd is therefore also Linux only, and its stubbornness in this respect has been a point of contention for some, and of contentment for others, such as one Lennart Poettering, the mastermind of this ordeal. The anatomy of the dbus. Image description. This image compares two calls which are effectively the same. One done via busctl, a generic dbus utility. The other done with systemctl, a Systemd custom CLI interface to perform the communication with Systemd, which ultimately resolves into calling dbus. Dbus's anatomy is as beautiful as the compositions of the young French composer Claude Debussy. It's a client/server architecture. One server, many clients usually. There are plenty of libraries to build dbus entities yourself. The dbus daemon runs a bus, a virtual channel where messages fly back and forth. Actually, there are usually two buses running on your system. The system bus, for system-wide services. This is where the big players hang out, Network Manager, and even Systemd itself, which is actually a dbus service this whole time. Surprise! The session bus, a private bus for each logged-in user, handling things like desktop notifications and application communication. When a program connects to a bus, it gets a unique ID like :1.1553, but since nobody wants to remember that, it can also claim a friendly, well-known name, aka a bus name, which by convention looks suspiciously like a Java package name. For example, org.freedesktop.networkmanager, UG. This is how you can talk to the Network Manager service without caring about its PID, its dbus ID, or what particular implementation of the dbus interface is actually running the client process. It's basically DNS for dbus. The above flexibility is part of the claim made that Systemd is just a collection of tools, and they are all replaceable. But naturally, no one does that because everyone likes to complain. But no one has a level of virtuous masochism that would make them want to replace even one part of Systemd. The real fun begins with the dbus object model. It's got a whole OOP-ish vibe. A service on the bus doesn't just send random messages. It exposes objects. These objects live at paths that look like file system paths, but are just a representation of the object's hierarchy. For example, org/freedesktop/systemd1. These objects have methods you can call and signals you can listen for, which are grouped into interfaces, again with the Java names, like org.freedesktop.systemd1.manager, but not to be confused with the dbus well-known name mentioned above, despite them being the same sometimes. Yes, I know, you lost the will to live by this point, but if you think about it, Every typed RPC protocol feels like looking at the void of the abyss. If you stick around, I'll show you a future where this might not be that much of a problem. This is getting way too abstract. You're probably thinking, fine, let's make it concrete. The systemctl command you use all the time is basically a fancy, user-friendly wrapper for making dbus calls. When you type systemctl start a cool app.service, you're not writing arcane magic. You're just sending a dbus message to the systemd process, PID1, which is a dbus service. In fact, you can do it yourself with the busctl tool. This command does the exact same thing. This bash code block is an actual example of the call to busctl. It's a regular call. It's only using an arguments variable so that I can add comments to each argument. As you can see, I started questioning my existence halfway through. Do you need to know anything at all about dbus to use systemd? Not really, but it helps to ground the monstrosity of it all. Before moving on, the winds of change are talking about a dbus alternative, Barlink. It's a newer RPC protocol that uses JSON instead of XML, but works basically the same. Fear not. It's been said that systemd deeply integrates with dbus, and that's not going to change anytime soon. Currently, systemd exposes its APIs both as dbus and as Varlink. Now that we got a taste of all sorts of Ds, let's go down the rabbit hole into the C. The ABC of systemd. Cgroups. Ever heard of Docker containers? They are how we solve the problem of running safe and isolated software on any OS. If the OS is Linux, use the containerization features of the OS. A key one, but not sufficient for full containerization, is Cgroups to run your software. If the OS is not Linux, run Linux in a VM and repeat the previous step. Easy. So, what are these Cgroups which found their way into the cornerstone of cross-platform software deployment? You can think of Cgroups, aka control groups, as providing a vital part of the full containerization experience, namely the isolation of hardware resources, CPU, memory, input/output, etc., between processes, and to keep processes somewhat isolated from each other. And, more relevant for us, systemd uses Cgroups extensively to provide a level of security and isolation to all processes on your machine. Basically, if your Linux has systemd, you can't escape Cgroups. Every single process runs in one Cgroup. Some Cgroups contain many processes. There is one Cgroup for each user and its processes, but if you use systemd services, each of them gets its own Cgroup by default. This is a huge win. In the old days, a daemon could fork itself into oblivion, detaching from its parent and becoming an untraceable ghost in the machine. You can get a bird's eye view of the whole Cgroup hierarchy with systemd cgls, or peek at the raw data yourself, since the kernel conveniently mounts them as a virtual file system under sys/fs/cgroup. Everything's a file on Linux, even your dignity. Example of a Cgroup hierarchy managed by systemd. Image description. The Cgroup hierarchy shows mostly Cgroups which contain other Cgroups. These are of type slice and scope. The systemd managers, global and per user, are also shown here. More on that later. Systemd organizes this hierarchy with its own naming convention, which also happens to correspond to its own unit types. More on that later, I promise. You'll see things ending in .slice, a group of Cgroups. Think of it as a folder for organizing other Cgroups, primarily for resource management. The whole system starts in the root slice, .slice, with user processes in user.slice and system services in system.slice. .service, a Cgroup for service unit, like your nginx.service. This is the most common one you'll see. .scope, a Cgroup for grouping foreign processes that systemd didn't start itself, but still wants to keep tabs on. Your user login session, for example, lives in a scope. But wait, you say, I see a systemd process nested inside another service. Yes, you found the nested systemd user instance. Each logged-in user gets their own private systemd manager that runs services meant for the user. It has its own dbus bus, and manages its own Cgroup hierarchy under your user slice. And yes, it's confusing that your graphical session apps live in a .scope managed by the main PID1, while other user background services live under the systemd user service. The rationale is, well, I want to believe there's a rationale. To clarify things a little bit, just as there is a systemd bus and user-specific dbuses running at the same time, there is a systemd and user-specific systemds running at the same time. You can get in on the Cgroup action yourself. The systemd run command lets you launch any command in its own transient.service or .scope unit, effectively giving you on-the-fly Cgroups. It's like your own personal nice or no hang-up. allowing you to set resource limits for a single command. Then there's the related systemd run 0, which is meant to become the new sudo, but we don't talk about that because sudo is a sacred spell passed on to us eons ago. Getting down on the D. Systemd units. Alright, we've met the referee, D-bus, and the field. Cgroups. Now it's time to meet the actual players. Sorry to American readers, we in the real world use soccer metaphors, we are manly like that. Even our women. In the world of systemd, everything is a unit. They are declarative little configuration files that tell systemd what you want done, not how to do it. You don't write a script that says start process A, wait 5 seconds, check if it's alive, then start process B. Instead, you create 2 unit files and tell systemd, hey, unit B needs unit A to be running first. Systemd cleans up the mess. It's like SQL for exercising your machine, but with no explain keyword. Now I know you can't wait to get your hands on a unit, but first let's explore the different types of units. There are 11 of them, but let's focus on the ones people actually use. Service. This unit type starts and controls a daemon or any long-running process, or any process you want really. It's the most common type of unit you'll write or interact with. Socket. This unit encapsulates a local IPC or network socket. When traffic arrives on the socket, systemd will activate the corresponding service unit. This is socket activation, an idea heavily inspired by macOS's launchd. It allows services to be started on demand, reducing boot time and resource usage. Likely the best selling point of systemd is how much of the system initialization can be done in parallel due to this. Target. A way to group other units and create synchronization points. Targets don't do much themselves, they are just hooks for dependencies. When you start a target, you're telling systemd to start all the units that are wanted by or required by that target. Some targets correspond to the old sysv init run levels. For example, multi-user.target is roughly equivalent to run level 3. In any case, targets usually encapsulate the units needed to consider that the boot process reached a particular milestone. On boot, systemd activates the default .target unit, which is usually the symlink to graphical.target or multi-user.target. Yes, this is Unix. We use symlinks to configure stuff, but also that's not the only way. Yes, this is tricky. We'll get to that later. Help, I'm trapped in a systemd article and I can't get out. Timer. For triggering the activation of other units based on timers. This is systemd's answer to cron. You can define real-time timers that run on a calendar schedule, for example, every Monday at 2 a.m., or minutonic timers that run after a certain amount of time has passed since an event, for example, 15 minutes after boot. Slice and scope. These relate directly back to Cgroups. A .slice unit is used to group other units together in the Cgroup tree for resource management. A .scope unit is used to manage foreign processes that systemd didn't start itself, but wants to track. Unit files. Image description. This shows the directories in which you can find user files. Note how they're a cross-cutting concern, such as system vs user and type of units. Units are configured in simple ini-style text files, a classic Windows shenanigan. These files live in a few specific places, with a clear hierarchy of precedence. For system-wide units, systemd looks in, etc/systemd/system. Highest precedence. For sysadmins custom units, symlinks to enabled units, and overrides. Run/systemd/system. For runtime generated units. User/lib/systemd/system. Lowest precedence. For units installed by packages. For example, via pacman or apt. The rule of thumb is, be like MC Hammer, and don't touch this. User/lib/systemd/system. If you need to change a package provided unit, you should create an override file in etc/systemd/system instead. We'll get to that. A unit file typically has 3 sections: unit, install, and a type-specific section like service or timer. Image description. Unit sections. The unit section. This section contains generic information about the unit and, most importantly, its relationship with other units. Description. A short, human-readable string describing the unit. This is what you'll see in the output of systemctl status. Once, a space-separated list of units that should be started along with this one. This is a weak dependency. If a unit listed in once fails to start, systemd doesn't care and will start this unit anyway. Requires a strong dependency. If a unit listed here fails to start, this unit will not be started. Furthermore, if a required unit is stopped later, this unit will be stopped too. In general, it's better to use once to build a more robust system. After and before. These define the startup order. After equals other.service means this unit will only be started after other.service has successfully started. Note that this is completely separate from once or requires. If you want unit B to start after unit A, you need to specify both a requirement and an ordering. Requires equals A.service and after equals A.service. Conflicts, the opposite of requires. If this unit is started, any unit listed here will be stopped, and vice versa. The install section. Enabling and disabling. Now this is where things get weird as fuck, so hold on. This section is not used by systemd at runtime. Instead, it's read by the systemctl enable and systemctl disable commands. It tells systemctl how to hook the unit into the boot process. So basically, it's a way of providing make me bootable instruction to systemd. But then it's up to the user to request to make it bootable. Making it bootable typically consists of saying which target this depends on using options in the section, which systemd will use to create some weird-ass symlinks in a particularly named folder which is equivalent to declaring the dependency explicitly on the target, except we don't do that because we want to keep the original target files clean. You got that? Good, you're starting to believe in the D. Wanted by. This is the most common directive here. Wanted by equals multi-user.target tells systemctl enable to create a symlink to this unit file inside it etc/systemd/system/multi-user.target.once/directory. This effectively makes our unit a dependency of multi-user.target, ensuring it gets started during a normal boot. I'm sorry, I don't like this any more than you do. The service section. The guts of the operation. This section is specific to .service units and defines how to run the process. Type. This tells systemd how to track the service's startup process. Common types are simple, the default. The service is considered started as soon as the main process is forked. Exec is generally preferred. Exec. What you wish were the default. The service is considered started after the execd system call has successfully completed. Forking. For traditional Unix daemons that fork a child process and then have the parent exit, systemd considers the service started once the original parent process exits. This type is best avoided if possible. One-shot. For short-lived tasks, the service is considered active until the main process exits, often used with remain after exit equals yes to make other units depend on the fact that this task has completed successfully at least once. Notify. The service is expected to send a ready equals 1 message back to systemd via the sd-notify library call when it's ready. This is the most robust way for a service to signal readiness. Dbus. The service is considered ready once it acquires a specific dbus name. Exec start. The full command, with arguments, to execute to start the service. Restart. Configures if and when the service should be automatically restarted. Common values are no. Default. On failure. If it exits with a non-zero code. And always, start limit interval sec and start limit burst, a rate limiting mechanism to prevent a service from getting stuck in a rapid crash restart loop. For example, start limit interval sec equals 10 and start limit burst equals 5 means systemd will stop trying to restart the service if it fails 5 times within a 10-second window. Execution environment. You can control the environment of the executed process with directives that are common to several unit types. Working directory sets the current working directory for the process. User and group specifies the Unix user and group the process should run as. Environment sets environment variables directly, for example, environment equals var1 equals foo var2 equals bar. Environment file specifies a file to read environment variables from. 1 key equals value pair per line. Overriding unit files. As mentioned, you shouldn't directly edit files in user/lib/systemd/system. The proper way to modify a unit is to create a drop-in file. Systemctl edit myapp.service is the magic command for this. It will open an editor for a new file, typically at etc/systemd/system/myapp.service.d/override.conf. In this file, you only need to specify the sections and directives you want to add or change. For example, to change the restart policy of myapp.service, your override.conf might just contain start of ini configuration file code block. Service. Restart equals always. End of code block. To clear a list-based option like once, you can set it to an empty value, once. When you're done, systemd merges this drop-in file with the original, with your changes taking precedence. After making any changes to unit files, you must run systemctl daemon reload to make systemd aware of them. Systemctl edit does this for you automatically. Spotlight on other unit types. Socket units. Socket units, or socket units, are the key to on-demand service startup. A .socket file defines a socket, and for each one, there must be a matching .service file, for example, myapp.socket and myapp.service. The .socket file has a socket section. Listen stream, listen datagram, define the address to listen on. For a TCP socket, this would be an IP address and port 127.0.0.1:8080. For a Unix domain socket, it's a file path. Run /myapp.sock, except, if no, the default systemd passes all listening sockets to a single instance of the started service. If yes, systemd accepts each connection itself and spawns a new instance of the service for each one. This requires the service unit to be a template. For example, myapp@service. When you enable and start the .socket unit, systemd creates the socket and listens on it. The .service unit isn't started yet. Only when the first connection arrives does systemd start the service and pass it the ready-to-go socket file descriptor. Timer units. Timer units replace cron. A .timer file activates a matching .service file. The timer unit contains a timer section with directives that define the schedule, real-time, wall clock, timers, use on calendar with a specific calendar event format. On calendar equals weekly runs once a week at midnight on Monday. On calendar equals 14000 runs daily at 2 p.m. On calendar equals mon2 *01.051200 runs at noon on the first 5 days of the month, if they are a Monday or Tuesday. Minutonic timers activate after a time span relative to a starting point. On boot sec equals 15 min runs 15 minutes after the system boots. On unit active sec equals 1w runs 1 week after the unit was last activated. Persistent equals true if the system was down when the timer should have fired. This setting makes it run as soon as possible after the system is next booted. You enable and start the .timer unit, not the .service unit it controls. You can see all active timers and when they're next scheduled to run with systemctl list timers. Controlling the system with systemctl. Systemctl is your command line interface to the systemd manager. We've mentioned it a lot, so here's a more structured look at its main commands. Unit inspection commands. Systemctl status unit shows detailed runtime status of one or more units, including its state, active, inactive, failed, cgroup, recent log entries, and more. If no unit is given, it shows the overall system status. Systemctl list units all type equals type, lists units that systemd has loaded into memory. By default, it only shows active units. Systemctl list unit files lists all available unit files found on the system and their state, enabled, disabled, static. Systemctl cat unit shows the contents of a unit file, including any drop-in overrides, so you can see the final, merged configuration. Systemctl list dependencies unit shows a tree of the requirement dependencies for a unit. Unit management commands. Systemctl start unit starts, activates one or more units. Systemctl stop unit stops, deactivates one or more units. Systemctl restart unit stops and then starts a unit. Systemctl reload unit asks a service to reload its configuration without a full restart. The service must be designed to support this. For example, via exec reload, systemctl enable unit enables a unit to start at boot by creating the symlinks defined in the install section. This does not start the unit right now. Systemctl disable unit, the opposite of enable, removes the symlinks. To do both at once, use the null flag. Systemctl enable null myapp.service. Systemctl daemon reload reloads all unit configuration files from disk. You must run this after manually creating or editing a unit file, but not when using systemctl edit. A quick look at the journal. The final piece of the core systemd puzzle is its logging system, the journal. The systemd journal daemon collects log messages from a variety of sources: curl messages, dmesc, standard syslog messages, the old system, cross Unix, extended and extinguished by the D, standard output and standard error from all services managed by systemd. Messages written directly to the journal API. All of this data is stored in a structured, indexed binary format in var/log/journal/. If configured for persistence, or run /log/journal/, non-persistent, it's also cryptographically protected to prevent tampering. The tool to read it is journalctl. Using journalctl, journalctl by itself will dump the entire journal, which is usually too much. The real power is in its filtering options. Follow logs live. Journal CTLF. Show logs for a specific unit. Journal CTLU engine x.service. Show logs from the current boot. Journal CTLB, or B-1 for the previous boot. Filter by time. Journal CTL since 2023-10-26 until 1 hour ago. Filter by priority. Journal CTLP error shows all messages with a priority of error or higher. Error, crit, alert, emerg. Change output format. Journal CTL overboth shows all structured fields for each log entry. Kernel messages. Journal CTLK is a shortcut for viewing just the kernel ring buffer. You can also use systemctl to pipe the output of any command directly into the journal. For example, ls of root pipe to systemctl with pinfo, and tmyscript will run the command and log its output with an info priority and the identifier myscript. This concludes our tour of systemd. God, I'm tired. From dbus IPC and Cgroup process management, to the declarative unit system and the structured journal, systemd provides a comprehensive, integrated suite of tools for managing a modern Linux system. While it has a steep learning curve and its share of controversies, understanding its core components gives you immense power and control over your machine's lifecycle. Now go sit back, relax, and drink the alcoholic beverage of your choice. You earned it. Thanks for reading. If you enjoyed the D as much as I did and want to support my writing, consider buying me a coffee at ko-fi.com/SebastianCarlos.